MIT class starting time. So let me welcome everybody out there on the internet. So presumably we are live streaming, we are. And let me just mention that next week there is no class on Monday at MIT. So Monday in Massachusetts and I think maybe New Hampshire, I forget where else, or Vermont, I think is Patriots Day. It's sort of a local New England holiday. Basically, lately it's been an excuse for the Boston Marathon, though there won't be any running of the marathon this Monday. But to make a long story short, no classes on Monday. The next class will be a week from today on Wednesday. Okay, so let me share my screen and mention that today's lecture is going to be kind of inspired a little bit by the last lecture on least squares, but with a different focus. So today's lecture is on optimization, which is kind of a big deal these days. I guess it's always been something of a big deal. So today's lecture is on optimization, and what I'd like to do is focus on a little bit of the math, but also the software for optimization. And I thought I would begin with a little story, which was when I was a graduate student, which was a long, long time ago. At least it seems that way now. When I was a graduate student, I was at MIT, and my roommate was taking a class over at the Sloan School. That's MIT's business school. And they were doing some sort of game of some sort, so some sort of negotiation game. And I tried to run an optimization back then to see if I could get a better answer than, I had the computer and nobody else would have had the computer. And I failed utterly. The software, I did everything right, but the optimization wouldn't converge. No matter what I did, nothing good would happen. So, excuse me one second. Sorry, everybody. I think my dog might have almost eaten some chocolate, and so that was a bit of an emergency in our household. So anyway, to tell my story, the optimization wouldn't converge. I couldn't quite get it to work, or it would just, it would go off to infinity, get nans, and part of that was a testament to the fact that the computers of the time were too slow to be useful. But you'd be surprised how often that still happens, even with the faster computers that we have today. All right, so to get things going, let me tell you some of the Julia concepts that we're going to be doing today. So I kind of outline them. So you'll see this as we go, but named tuples are just a fun little data structure that I would mention so that you could actually give a name to the first and second entry, say. It doesn't have to be size 2 for tuples. I guess the big story, maybe this is worth saying a few words about, is function of functions. And so when you run optimization, what you're doing is you've got a function and then you're trying to put something around it, right? Automatic differentiation is another thing where you've got something happening, you're putting something around it. And those are the sorts of things that are really more enabled with today's computing power than they really ever were in the past. And I will talk about some software packages, which is, for example, Optim.jl, which will perform optimization in Julia. And it's completely written in Julia, and that actually has some, the fact that it's written in all Julia actually has some value to it, as opposed to sort of a mixture of programs. And I'll also mention JuMP, which is a very popular modeling language. And JuMP is really kind of gotten, it's really sort of been spread around the world, partially in the business schools, also for other purposes. At MIT Sloan School, JuMP is used quite a lot these days. And so I'll mention something about that. But I decided to kind of, in today's lecture, I didn't want to get too complicated. You could really do some really complicated optimizations, but I decided to start with kind of a simple problem, the line fitting problem that we were talked about on Monday, but I wanted to do it many, many ways, right? So a simple problem that could be done a lot of ways. And I just wanted to kind of talk about the different ways, because for me, I thought there was something very interesting about just taking a simple problem and doing it a lot of different ways, and kind of seeing the pluses and minuses. Some of the ways generalize better. Hey, Phil, I hope you're okay. All right, so some of the ways generalize better, some of the ones run faster. So let's take a look. So we're going to do some exploratory data analysis. So I'm not going to play with the ends too much right now because I'm actually running so many optimizations that if I change n, it'll take a while. Though I mean we could change it a little bit. But I'm going to take the centigrade Fahrenheit data from last time and add a little bit of random noise. In this case, I'm taking a standard deviation 5. And so there's the theoretical line that connects Fahrenheit to centigrade. And I'm just sort of bouncing it around a bit with this 5 times rand n. And I happen to take, for whatever reason, 23 data points. I guess I could take more or fewer, but I'm a little worried about how long it'll take. I'll up it to 33 and we'll see what happens. It might take a little while to catch up with me. But anyway, this is the data we'll work on. And of course, what I want to do is find the least squares line again. And I'm going to do this, such a simple problem that you'll see in many, many courses. And I'm going to do this many, many ways. So first of all, let's express the problem clearly mathematically. What does it mean to find a least squares fit to a straight line? Well, we have this data, these red dots, okay, and these red dots have x coordinates, so we'll call that xi. Now maybe it would be, yeah, so I have my data in this x vector, and if I have an intercept b and a slope m, that is by definition the best straight line. Okay, so basically says that I can call the first thing first, the second thing actually captures the words first, next, last. It actually keeps a Julia symbol appears with a colon in front. So that maybe this is worth telling people about. So for example, I can make a symbol just by putting a colon in front of anything. So colon, hello, internet world, right? And that's a symbol. Okay, so here, let's call this thing S equals maybe. And then I can go type of S and you'll see that it is, oops, I have to spell it right. Type of S, and you'll see it's a type symbol. Okay, and so I like this mainly because I can print this out just like, and then I can see B equals M equals. So just for displaying it for me personally, I like these named tuples very much. Okay, so there's just a tiny little bit of Julia, and also, one simple looking formula for computing the best slope and the best intercept for a straight line. There's also the linear algebraist formula, which is even simpler looking, but you need to know a little linear algebra to make some sense out of this. But this is basically just so, in case you're curious how this works, this matrix over here is a 2-column matrix. Let's print it out. The first column is all ones, and the second column is all the x coordinates. And it's okay if there's repetitions. It actually doesn't cause any trouble at all. In fact, if you had, you could imagine that you took 2 measurements where the Fahrenheit was -9, you could even get different centigrade measurements, and it'll try to find something reasonable to do with that. So the only thing that's actually required of least squares is that there is at least 2 distinct points, right? 2 points determine a line. Other than that, you could have 100 points, but you have to have at least 2. Other than that, this code will work for any set of data. So that's this matrix. Y is the Celsius data, and this backslash says find the best combination of these 2 columns to give you this column. All right, so again, maybe you know what this means, maybe you don't, but these are 2 direct formulas that are sort of easy to type. Okay, so now we're going to move on to sort of much more complicated ways to solve this problem. In fact, you'll wonder, why am I doing it to solve such a simple problem? I'm about to find more complicated ways to do it. And these more complicated ways, they actually take a lot more computer time, right? So it seems like there's nothing good about these ways. except that they're going to generalize to much, much harder problems, right? And so this is sort of typical that you can have these nice exact formulas for simple problems like fitting a line. I mean, you could generalize this a little bit to fitting quadratics or even fitting a little bit more, but ultimately what we want is much more general approaches. And so this is why we're going to get into optimization methods. And so I want to share with you the Optim.jl package, which is a Julia package, which is written entirely in Julia from top to bottom. So this is completely in Julia. And I'll just point out that you can literally ask the software to solve this exact problem. By the way, it's worth mentioning that it's very often the case that we don't want the minimum, but rather we want to find where the minimum happens. In my own experience, I almost never really need to know what the minimum is. Maybe some people do, but it's always my experience is that I want to know where it happens, right? I don't really care what the sum of squares is. I want to know the best intercept and slope, right? And so, so a lot of software recognizes that this is what people want. And so let's put the thing that we're minimizing into a function. So let's call this a loss function, because this is what everybody in the machine learning world is doing these days. So we have this function here, the thing that starts with the summation and goes to the end of the line. We could write it in Julia language as, the sum of b plus m xi minus yi squared for I equals 1 to n. Okay, and notice I didn't have any square brackets. This never creates or stores a vector. It actually just simply sums this up with very little memory. Okay, and then if we want to optimize it, it's actually this easy. You just go optimize the loss function with some starting guess. And so I guess I could have done a random intercept and slope. I decided to start at 0 for no reason whatsoever. And we could see that the minimizer came out. Hopefully it's the same as the B and M that we had before. Maybe I should put it over here so we could see what it looked like. So what did we have before? We had B equals B and M equals M. Hopefully it's, there we go. And oh, isn't that nice? We got the same answer with this optimization routine as we got with the exact formulas. That always makes me feel good. Okay, so it looks like to at least 5 places or 6 places, they look about the same. Okay, now of course, optimization programs there's a lot going on. It's sort of a long story. In fact, it's kind of cool that you could just run optimize function with some starting guess and get an answer. Lots of things happen. First of all, it kind of told you that, yay, we got the answer. It did tell me the final objective value, not that I really cared as much about what the sum of the squares was. It chose an algorithm for me. There's this algorithm called Nelder-Mead. If you ever take an advanced numerical class, you might learn how Nelder-Mead works. But the key point is that I don't have to supply extra information. And Nelder-Mead sort of the algorithm that works where I'm just going to, when you just want to type the function and not give any more hints other than a starting guess, Nelder-Mead is good. It's telling you that it's checking for convergence by checking that somehow the average square root of sum of squares is small enough. This is to 8 digits of accuracy, and maybe more important is to see how many iterations, or perhaps even better, how many times did you have to call the loss function? So this is actually a really important measure of how much complexity your optimization program needed to get to 8 digits, right? And so in this case, we had to calculate the loss function 136 times. Whether you think that's a lot or a little might depend on just how much work your function requires. I mean, this function is pretty simple. It's the sum of squares. A lot of times functions have a lot more complexity to them. But here you see we were able to run this thing readily and get the same answer we got with the exact formula. Okay, and I started to mention this function of functions at the beginning of the lecture. I feel like this is worth repeating that optimization of a function, such as minimization of this loss function, it's really a fairly heavy function of a function. And by function of a function, I meant that we input a function and we're going to put something around it, right? We're trying to find something about this function. I mean, this is the sort of thing that as I was mentioning at the beginning of the lecture, was fairly hard to do on important real problems. It was actually fairly almost impossible up until maybe 5 or 10 years ago. Of course, it keeps getting better. We could get increasingly more and more complicated problems. But it just was hard to get this kind of stuff done without the modern computing power. And so the fact that we can nowadays do this sort of thing, it kind of energizes the ability to do machine learning, as well as other simulations that people want to do. And so it's this modern computing power has really kind of found a place for optimization. And so by heavy, I'm talking about the large amount of computing power that's often needed to get to an answer in a reasonable time. All right, so I would say optimization is really the thing, for this decade, really, this and last decade, maybe. Let me also mention JuMP, which stands for Julia for Mathematical Programming. So JuMP is another package, which it's some people think of it as an optimization package, but it's really a modeling language package. What it does is it lets you express many kinds of optimization problems in a language that's somewhat mathematical, right? And so maybe I'm using a fairly simple function here just to show you how it would work, but basically it's a language. It's actually it actually uses Julia's abilities to basically write domain-specific languages, and so optimization is kind of a domain-specific language, if you will. So many people are using Julia in that way these days, and the actual optimization in this case is going to be is actually selectable, and we're going to use a package that's not written in Julia to do it today. I'm going to take IP.opt. So IP.opt is a open source package not written in Julia, but it's sort of relatively compatible with JuMP. There are a bunch of other choices as well. So I'm going to take the IP.opt optimizer, and I'm going to say that my two variables that I want to optimize are B and M, and that's how you express this in Julia. You say add variable model B and model M. And I'm going to specify that my objective is to minimize. By the way, you might have noticed I never told optimize to minimize. That was the default. But in JuMP, I'm actually saying explicitly, I want the minimum. I don't know, does it work if I don't actually say that? I have a feeling it breaks, but let me see, I don't even know. Yep, it doesn't like that. It wants to know. So I'll put the minimum back in. So minimize the sum of the squares. And then I could just say optimize the model. And hopefully I get, again, with the JuMP program, I get the same answer we got before. Let's see, there it is. You can check up here that this is the same numbers as down here. Okay. So some of you may see JuMP in other classes, or you might have uses for doing some very fancy optimization. And JuMP seems to be the way to do that these days. It's gotten quite popular for that. So I wanted to show you this. But what you might wonder is what is, when you're doing optimization, you may have seen this already, that when you do optimization, the thing to calculate are gradients, right? And so if you do machine learning, you'll hear about stochastic gradient descent. We'll give you an example of that in a little bit. I have it over here in the table of contents. So gradients have somehow become much more popular because of machine learning. I often repeat that around computer science at MIT, I used to never hear gradients except for maybe people doing graphics or robotics. But other than that, the word gradients was somehow never said, or not to my experience. But nowadays, gradients are everywhere because machine learning is everywhere. So let's talk a little bit about what is a gradient, how it's used, and how it accelerates optimization. right? So let's do that. First of all, we do require 1802 to be simultaneous, so we assume that you actually know what a gradient is, but just in case you've forgotten or haven't seen it before, let me tell you. We've got this function here, right? The sum of b plus mxi minus yi squared. And remember, there's a lot of variables here. There's b, there's m, there's x and y. But I want you to focus on this as a function of just two variables, the intercept b, the slope m, right? The xi and yi are like parameters. They're kind of like constants for this entire story, right? But the b, this is a function of two variables, b and m. And so it's completely reasonable to take the derivative with respect to b and also to take the derivative with respect to m. Okay, and this is easy to do because this problem's not very complicated. Actually, the sum kind of goes for the ride. The square comes out and gets a 2 in front. And when you take the derivative with respect to b, you know, when you have a square, you have, it's just, the derivative of something squared is twice the something, right? The derivative of b is 1, so it's just twice the something, right? When you have the respect to m, it's twice the something, but also times xi. And so if you look closely, you'll see the difference between this answer and this answer is just the xi over here. Maybe I'll make it bigger. And can I make it bigger? Come on, get bigger. There we go. It's tempting to make it bigger and just sort of focus on I could use Zoom's annotate to emphasize that the only difference between the derivative with respect to b and m is that when I take the derivative with respect to b, I get 1. I take the derivative with respect to m, right? The xi comes out from here, right? But you all know how to take derivatives. That's nothing fancy. So for this problem, taking the derivative is easy. So let's just do it. And what I'm going to do is put it into Julia software. First, I'll do it without the summation, and then I'll sum them up. So let's use the math symbol for gradient is this nabla, the upside down triangle, the thing that means harp in Greek or something. So this gradient of the loss function with the ith term in the sum is exactly 2b plus mxi minus yi. And I'm going to treat this as a vector. So I'm just going to multiply this one by 1 and this one by xi, which will get me the one term from here and one term from here. And then the actual gradient will be the sum of these vectors. Okay, this will be handy because sometimes I'm just going to want the ith term anyway. And so this is a hand computation of the gradient. And this is the sort of thing that people used to do up until about 5 or 10 years ago. I mean, some people still do this. You work out the gradient on a piece of paper. Maybe you on the back of an envelope, they used to say, or whatnot. Maybe these days you would open up a symbolic program to do it. But in any event, this is how it used to be done when it was reasonably possible. And of course, the other thing that people might do would be a finite difference evaluation for the so here's the explicit answer, and just to pick a numbers, I evaluated at 0.1 and 0.3. This is the b and m. I just took these numbers, and the other thing that you might do if a hand computation was too hard would be to add a little epsilon to the b and add a little epsilon to the m. Right, this is what a derivative is, right? And subtract the value. Perturb the first coordinate, perturb the second coordinate, divide by epsilon, take a small epsilon, and if you take epsilon small enough, you'll get a good answer, right? If I take it too large, well, it's good to what? 2 decimal places. If I take it a bit smaller, this one is good to the number of digits displayed. This one is getting there, but still not quite there, right? So you can, I could take epsilon smaller. You go too small and you run into rounding errors. I haven't tried that, but I imagine that's what will happen. Yeah, see, once you take epsilon, in math, we talk about the limit as epsilon goes to 0, but on a computer, floating point error will kick in, of course. And so you don't want to get too greedy. And so finite differences are a little bit nuisancey because you never know how far to go, right? You want to go far enough to be useful, but not too far to bump into rounding errors. Yeah, we'll stop there. Maybe one less. Oh yeah, even better. Okay, I was already having some rounding error. Okay, so finite differences have their problems. I mean, they're they're a time-honored way of computing derivatives and gradients, but they're not really the best way. And nowadays, the automatic differentiation methods have really come in their own. And maybe one of the key things I can tell you about automatic differentiation today is that it's neither a symbolic or hand computation. Well, it's certainly not a hand computation, but it's not a symbolic computation. It's not the sort of thing that like Mathematica would do when it computes gradients or derivatives. And it's not a numerical difference either. It's not one of these, perturb the function. It's certainly not of this kind of ilk where you'll have a rounding error because you did it this way. It's something else. If we have time, maybe today we'll talk about what it is, or maybe in a future lecture. But I think we showed this in a previous lecture, and I'll just kind of call the routine, that in Julia, you can basically surround any Julia function with a forward diff. Say, this is automatic differentiation comes in sort of forward mode and reverse mode, and sometimes one is better than the other. But I can evaluate the loss function at point 1.3, and I can evaluate the derivative by some sort of automatic differentiation magic of some kind, and you could see it gives the right answer. So let me emphasize something that I mentioned before, that optimization was a function because I surround a function. And again, and so is automatic differentiation, right? You see, I've got a function and I surround it with the gradient calculation, and hopefully it will just work. And in a way, this is where computer science and language is probably well more relevant than mathematics. We often think of derivatives as a mathematical idea, but the ability to be able to surround an arbitrary code, possibly filled with if statements and so which we often think of as discontinuities, and maybe it might be an iterative calculation. So theoretically, it takes infinitely many steps to get to an answer. To be able to do all of these things and just surround it with a gradient is quite magical. But really, what it is it's computer science much more than mathematics. It's the ability to be able to get your language to let you do what in your mind is so obvious, right? In your mind, there's some function here. Let's take its derivative, okay? But to get a machine to do that, and to do that all the time, that's a big story, and that's pretty exciting when that's happening. Okay, so here's one example. There are other examples out there of people doing automatic differentiation. That is the big software story of these days, I think, of being able to do this automatically. Okay, so now that we've got our gradient, why am I telling you this? Why am I telling you about gradients? Well, in part, I wanted to tell you about automatic differentiation a little bit, but really the reason I'm telling you about gradients is because we want to use gradients so that we can put them into optimizers, or maybe we can even do the optimization itself. And there's a method that one could write directly. I'm not going to call any package, called gradient descent. But it's actually remarkably hard to get gradient descent to work on real problems. So gradient descent is something that sounds like the sort of thing you might learn in a math course, where if let's say it's a function of two dimensions, your height. You could think of a skier on a mountain. People always have these analogies. You're on a hill, and the negative of the gradient tells you the maximal direction to go down. So you go down a little bit, and then you turn, and then you recalculate the maximal direction, and you ski downhill. Okay, so some of you may have seen that. It's actually quite tricky to do that. For example, it's easy to find the gradient. So here, I'm going to have an iteration where I'm going to find the gradient. Okay, so this line is easy, and this line is easy, but this line is going to be magical, and I'm not even going to explain it today. So this line is calculate the gradient. Okay, and this line says that I'm going to move in a direction of my gradient. Okay, I'm going to calculate an amount to ski downhill in the direction of the gradient, and then I'm going to start all over again. Okay, and the problem is, what is the step size? How far down should I go? And I'll tell you, I tried here. This is close to the right answer. You might remember that this is, oh, here, this isn't even that close. Maybe I should go more steps. Let's see if I go 50 steps in that direction. See, it's really hard to get the right answer.
I think you just need a very large number of steps.
Well, I don't know. My ski pass won't let me go that long. I don't know. No, I think I'm stuck. Really, a large number of steps? It looks like I've converged to the wrong answer. That's interesting because what I had done was I tried. Yeah, I don't know why I'm not getting the right answer. But yeah,
You try different starting guess?
Well, I could try. I guess I could try rand of 2 or rand n of 2. I don't know what that would do. But maybe this proves my point that it's so hard to get. Oh, you know what? I didn't think I'm hoping for this. This was my previous. Oh, maybe this is the right answer. Hold on. This hoping for was based on a previous version. Yeah, I shouldn't have done that. I should have gone.
You need to interpolate the values of b and m in that.
Exactly. So maybe I did have the right answer and I didn't realize it. So yeah, and this will be the right ones, right? Because I have the let statement. It won't go outside the cell. Oh, I can't do it like this. No. Why can't I get the B and the M? Well, let's see. Well, anyway, I am getting the right answer, so maybe that's all that I really need to know for now.
Can you remove the
tuple?
Yeah.
Why is that mattering?
I don't know what's going on there.
Yeah, no, this is. I don't know what's going on either.
Do you have variables called b and m?
Yeah, look, right there. I don't know what's going on, but don't worry about that. Here, let's concentrate on the key part. This was working. I just had mistakenly, silly me, hardwired. Yeah, it works from 0 as well, and it probably works with 25 steps. Yeah, 19.763.6152. Good enough.
What happens if you just take an eta that's a constant?
So I tried that, and it wasn't very successful. You have a favorite eta or eta or whatever?
1e minus 5 or something? 1e minus 3, yeah.
You see what happens? It blows up. This is what I'm saying.
Yeah,
these things are very sensitive to...
Now you need more steps.
Oh, really?
For small eta, you need more steps. Much more steps, like 10,000 or something.
10,000 steps. Still no good. I'll add a...
Yeah, that's close.
It's getting there. 100,000. There we go. Yep, lots and lots of steps.
I mean, that's what machine learning people do, right?
Right. This is what they do. This is art.
Train their model for days and days.
Yeah, and they fiddle with, and some people fiddle with the eta. Some people are trying to figure out how do you get the right step size. Will this still work? Oh, see, that's nan.
Yeah, I mean, that's strange.
Yeah, no, it's not strange. It's related to the fact that this stuff is very, very sensitive. I mean, if
I don't see why it should be.
Computers, I don't know. I mean, my experience is every time I try to.
Oh, is it to do with the way you're calculating the loss function? Because once you get to the local minimum, then you're dividing by 0.
Oh, you think because I didn't do a proper stop? Maybe that's it. But anyway, I could feel. I mean, I just went to 100,000 when I really should have tested if my thing was good enough, and maybe I would stop.
You're not dividing by 0. No.
Yeah. All right. Anyway, we could have fun playing with that, but I still maintain that this is not a bug so much as it's typical of optimization software. And I felt like when I was a graduate student and I first tried this stuff, I was naive because, I thought you could just sort of feed it to an optimizer and it would magically work. And as I've gotten more experienced and older, I find that it doesn't seem to always happen that way. In fact, more often than not, it doesn't work until you have to babysit it a little while and control it a little bit. And the good news is nowadays with faster computers, you can get this to work. Now, what I did over here is
and more sophisticated algorithms.
there's that too. So what I did over here to make it a lot fewer steps is because this was a simple function, I could actually figure out if I point my skis down the hill in a certain direction, I could actually figure out where the optimum is. That it's called a line search. It's a one-dimensional optimization, and I could find the exact place. And I just sort of worked it out and typed in this formula. And with an exact line search, which is almost impossible to do in real problems, but because this was a kind of toy problem, I was able to directly get the exact answer. So this is gradient descent, and it's a very simple method for finding optimization. You see, I didn't call any fancy programs. I'm literally, here I am at at an intercept and a slope, and here's my gradient, right? Here's the minus is the minus gradient, and I'm just going to take a step of size eta, and that'll be my new position. It's nothing more than just moving in the direction of the gradient, and then the art, as much as science, is to figure out how far to go, right? How much distance in the direction of the gradient should I go, right? And again, people have suggestions. There's all sorts of things you can do, but in the end, I think it's still art than science. Maybe, but this is the point of this is that you could see an entire gradient descent algorithm in front of your eyes. There's no packages, there's no other software. It's just an iteration with 3 lines of code. Compute the gradient, decide what step size to use, either something complicated or, as Dave was suggesting, a simple constant step size, and then update your position, right? What could be easier? Okay. Now what people do in the machine learning world these days, they don't do gradient descent. They do stochastic gradient descent, some sort of randomized gradient descent, because usually these functions are complicated and involve a lot of data. And so what they do is, instead of taking a step fully in the gradient direction, rather what they do is they update one or more coordinates at a time. But not all of the coordinates that they have available. And so I'll show you how that works. So here is stochastic gradient descent. And you can see I ran it 10 million times to get the answer, but at least I am getting the answer. 10 million times does take a long time to run, but at least if this was a big problem, it will run, as opposed to entire gradients, which may be impossible. And so what we're doing here is that it's a very simple looking code. Here I am, I'm starting at the position 0, 0, okay? I'm hoping to find my way to something like this. Well, this is, actually the M is a little bit off, but this is where I'm hoping to find my way, right? So I'm starting at the origin, and I'm taking, in this case, it looks like 10 million steps, and I'm hoping to find my way here, and I'm getting here to a few digits. Maybe it would be nice to get more digits, but I am getting there. I don't know what would happen if I took 20 million steps. We could try that, see if it gets a little better while I'm waiting. 20 million steps can take a while. You definitely don't want to do this in a slow programming language, by the way. Let me tell you what the idea of stochastic gradient descent is. The idea is that we are going to randomly decide which coordinate we're going to update, right? And so if you remember my definition of the gradient of the loss function, in fact, maybe I'll go back there if that's okay, where I first defined the gradient of the loss. There was actually a reason, there was a method to my madness of why I defined it with 3 arguments before 2 arguments. So here, the gradient itself is a sum over all the n coordinates, okay? And the coordinates of x and y, the parameters, and the ith one is just the ith summand, right? And so it's like a piece of the gradient. It's kind of a partial gradient, if you will. It's the gradient that's relevant for the ith coordinate, okay? And so you do that because in real world problems, the data is just too big, okay? And it would take forever to do the update. And this has been observed to work very well. And so what I'm saying is, of the n x's and y's, pick a random point from your data, just any old random point from your data, and take the piece of the gradient that corresponded to that one point, right? You could, I mean, there's nothing stopping you from actually summing up a few different points, right? I mean, I could have actually, I guess I could try this. I could sum this, you know, for I equals 1 to 3, right? And I mean, I might get a double, but maybe that doesn't matter. Let's see if this works. I've never tried this, but I would think it would work. And so here, what I'm doing is I'm taking three points at every step to, oh, I wonder, sum or mean? What's the right way to do this? I think I'm doing it with a sum. All right, well, 20 million is a long time. Maybe I should have taken something smaller. But I do think this will work, or at least we'll get to a few digits. Maybe the other thing to realize is, for most machine learning problems, people don't care about 5 or 6 or 10 or 20 digits. Very often, 1 or 2 digits is even 1 digit is quite enough. And so that's the beauty of all this. If all you really want is 1 or 2 digits to get your, you know, to get your fit, then it could be done very, very quickly. All right, well, I'm regretting running this 20 million times. Where was that? Yeah, I'm going to regret that, but it's okay. I'll let it run for a little while and we'll see what happens. Okay, I've got about 5 or 6 minutes left in my microcentury for this lecture. So the last thing that I think I'm going to do is just show you that, oh, okay, here we go. We got an answer. How good was it? 19.7. Well, it's trying. That's all I can tell you. It didn't even seem like it was as good as just taking 1. So I think I'll remove it. And we could just run this 20,000 times. And, oh, this is a horrible answer. Yeah, you really, Dave is right. You really have to run this a lot of times, even to get.
Yeah, I mean, there's an interplay between the size of the step size and the number of times you have to run. I mean,
Yeah, I mean,
what happens if you try a bigger step size and fewer?
A smaller number. We could try it. Oh yeah, that's pretty good. And if I have an even bigger step size, nope.
Yeah, then that goes wrong. That's weird.
Yeah, no, lots of things are weird about this stuff. You think that if I actually wanted it to converge, I mean, here I have the benefit of knowing the answer, but in the real world you wouldn't. Right. I could go fewer step sizes and make bigger steps. No, it's not gonna work. It's just not gonna work. So here, let's keep it at this step size and do 20,000, and well, maybe even a few more steps would be good. Yeah, the M isn't that great. If I made it a little bit smaller, no, that's worse. I made it a little bit bigger, oh, that's worse, even worse. Yeah, you see the game. This game, it's random, right? So every time I run it, I'll get something different. It's doing fairly well on the intercept. It doesn't really. Seems like the slope it's struggling a bit more. So yep, this is the nature of the thing. People are running the stochastic gradient descent a lot these days, and in the end, you get an answer. Maybe it's even hard to interpret. I mean, people are trying to figure out some theoretical analyses of these things, but I think it's pretty safe to say that this whole business remains fairly experimental in machine learning. You try this sort of game, you run the stochastic gradient descent, you get your parameters. They're not the slope and intercept of a line. They're the parameters of a neural network. But the idea is very much the same. You run it and you decide afterwards whether you're happy with what you got, because it could tell the difference between an apple and an orange, or a basketball and a football, or more complicated things. All right. Well, in the last couple of minutes, I thought I'd show you a few more arguments to optimize. This is the Optim.jl. Of course, you can go to Optim.jl. You can go find the docs yourself. Here they are, and read this a little bit. But I just thought I would. There's tutorials here, so you can kind of look at this if you like. But I just thought I would show you some arguments. So for example, you can specify an AutoDiff, which could be forward, or I think it's something like finite differences or something. So you could specify that it will calculate the gradient for you. There are methods out there called BFGS, which is named after 4 mathematicians, Broyden, Fletcher, Goldfarb, and Shano. So these are the folks who came up with this method a long time ago. Let's see if we can see the year. 1987. Oh, that's just a textbook, so it's probably the idea is even older than that. Yeah, so the textbook's 30 years old. I think the idea is much older than that. So, and you can, if you want to, what you could see that compared to my 20 million stochastic gradient descent approaches, this one only had 5 function calls. And so, and it gave the answer, I guess, to 8 decimal places. We can take a look, in 5 function calls. And so you can see where clever mathematics can help compared to random stochastic, gradient descent. However, this sort of method will not work very well on the huge problems of, with machine learning is based on tons and tons of data today. And these problems, these approaches just aren't suitable for huge problems, but they work great on smaller problems. And so you can see what it is we're missing in a way by not running these kinds of methods. Here's one where we don't use the AutoDiff, and so it has to attempt to calculate the gradient. And so, but still not too bad. This magical BFGS thing is converging in 11 steps. Here's another one I thought I would mention is you could actually tell it to do gradient descent. And at the very least, it's doing a better gradient descent than I'm doing. It's not running it in millions of steps. It seems to take 252 function calls. It looks like it's 56 iterations, 4 function calls per iteration. So again, it knows something that I don't. And that's sort of the real benefit for packaged software, because you get to capture the intelligence of people who've worked on this for years. Okay, and here's gradient descent where I actually give it the gradient, and it didn't seem to change much. I don't know. It shaved off 2 iterations. Don't really know what it's doing. Saved about 8 function calls. But anyway, I think I just wanted you to see that that there is this kind of software out there, and it can work pretty well. All right. So what have I done in this lecture, kind of to sum things up? That I took this least squares not because anybody would ever use optimization for software on least squares, but just because it was a simple function that, if I wanted to calculate gradients or exact line steps, I could just do it on a piece of paper, and I could at least sort of show you how it would look. We actually got to play with some Julia packages. We got to play with Julia's name tuples data structure, and kind of get a little bit of a peek as to what machine learning software is doing these days, kind of on the big, but doing it with a small little problem. Okay, so I think my microcentury has come to an end, and I want to repeat that next week's class, the next class will be next week on Wednesday, as Monday is going to be Patriots Day in Massachusetts. Normally the running of the Boston Marathon, but unfortunately not this year. But nonetheless, still an MIT holiday next Monday. So for both MIT students and everybody out there, if you're going to join us for the next lecture, that will be Wednesday. Okay, see you all then.